So finally, we'll look at Avogadro's law. Avogadro's law is what is going to allow us to incorporate moles into our gas calculations. So Avogadro's law, we're going to assume a constant temperature and constant pressure. So that means we're going to be looking at volume and number of moles. And intuitively, it should make sense what the relationship is going to be here. If you have more moles of a gas, more of the gas, then the volume is going to get larger. So we have a direct proportionality. Volume is proportional to number of moles. Or we can say that volume is equal to K times N, or we can go through the same types of rearrangements and substitutions that we did for the previous gas laws and say that V1 over N1 equals V2 over N2. And that's the form of Avogadro's law that we're going to use. Now, what will this allow us to do? If we look at a reaction like the following, nitrogen plus hydrogen react to form NH3. And if we say now that we have 2.4 liters of H2 and an excess amount of N2, how much NH3 will that form? So a couple different ways to do it. One is if we know our conditions. Say, for example, we're at STP. STP, defined as standard temperature and pressure, means we're at 0 degrees Celsius and 1 atmosphere. So if we knew that, our conditions, then we could use the volume of the H2 to find the moles of H2, to use our stoichiometric coefficients to find the moles of NH3, and use that to find the volume of NH3. It turns out we don't need to do any of that. Because there's this direct proportionality between volume and number of moles, all we need to do is take our 2.4 liters of H2 and use our coefficients. 2 moles of NH3 can be formed from 3 moles of H2, which means that 2.4 liters of hydrogen will allow us to form 1.6 liters of ammonia. All right, now finally, we're going to put all of these gas laws together and look at what is known as the ideal gas law. The ideal gas law, pressure times volume equals number of moles times this ideal gas constant times the temperature. The reason we can do this is if you think about what we've been talking about throughout this chapter, we know that volume is proportional to the number of moles and to the temperature. we also know that volume is inversely proportional to the pressure. So if we put all of this together, we could say that volume is proportional to N times T over P, and then we just need a constant to make it an equality. So V is equal to N times T over P times a constant K. What we do in the ideal gas law, because this is a very specific constant, this constant K becomes R, and this is known as the ideal gas constant. And this is the form of the ideal gas law that we use. PV equals nRT. So what's the value of R? Well, if we take our ideal gas law and we rearrange this, we solve for R. R is equal to PV over N times T. Now, if we go back a couple pages here to where we defined this STP, standard temperature and pressure, the second piece of this standard temperature and pressure, and this is going to help us out here, is at STP, 1 mole of an ideal gas will have a volume of 22.4 liters. So now if we come back to our expression here, we can use STP to plug numbers in. So STP, again, 1 atmosphere, 0 degrees Celsius. So we can say 1 atmosphere times 22.4 liters over 1 mole times 273.15 Kelvin. And if we calculate that out, we get a value for R, 0.08206 liters times atmospheres over moles times Kelvin. Now, one of the things that this does mean, unlike all of our other gas laws where we said we could use any units as long as we had the same units on both sides, that's not the case for the ideal gas law. Because in the ideal gas law, we have a constant that we use, and there are other values of this constant with different units, but this is the most common one, and this is the one I'll use for any practice that we do. If we use this value of the ideal gas constant, then we have to use liters for volume, atmospheres for pressure, and moles and degrees Kelvin. So basically we get to a point that we can solve for any of pressure, volume, number of moles, or temperature as long as we know the others. Because you can take this equation, again, here's where we're starting, and you can solve it for any of these terms. So you could say pressure nRT over V, volume nRT over P, number of moles, PV over RT, and even temperature PV over NR. But this ideal gas law allows us to do a number of other things as well. For example, we could ask, how many grams of argon are present in a tank that is 14.6 liters in size at 25 degrees Celsius and 995 torr. So you might be asking, how do we find grams? That doesn't show up in the ideal gas law. And it doesn't. But because we know what the substance is, we know that it's argon, number of moles does show up in the ideal gas law. So if we solve for number of moles, then we can use that with the molar mass of argon to find the number of grams. So let's do that. So we'll start by rearranging number of moles equals PV over RT. So our gas constant R, we can just go ahead and plug that in. The volume we can also plug in directly because that was given to us in liters, so 14.6 liters. The other two units, though, we're going to have to do a conversion. Because our temperature was given in Celsius, 25 degrees Celsius, so we have to convert that into Kelvin, so 298.15 Kelvin. And then the pressure I gave in torr, so 995 torr, 1 atmosphere is equivalent to 760 torr. So that converts to 1.31 atmospheres. And we can plug that in up here. All right, once we run through the math, we get that N is equal to 0.782 moles. All right, we're not done though, because the question asked for how many grams. So finally, we can take those moles, 0.782 moles of argon, and just do a moles to grams calculation. So 1 mole of argon is 39.9 grams, or 31.2 grams of argon. All right, let's see another thing that we can get from the ideal gas law. Calculate the molar mass of a gas if 0.23 grams have a volume of 125 milliliters at 298 Kelvin and 775 millimeters mercury. So your reaction to this problem, at least initially, might be, how do I calculate a molar mass? Well, in order to do that, we need to think about what is a molar mass. And molar mass is what allows us to relate number of moles to the mass of the substance. So our number of moles, we've done this calculation many other times in our stoichiometry chapter. We know that the number of moles is just the mass over the molar mass. And just so we don't have to keep writing this out, I'm going to abbreviate that as MM. So if we have our ideal gas law, PV equals nRT, and we now know that N can be mass over molar mass, we can rearrange this as PV is equal to mass over molar mass times RT, and I'm just going to grab this equation and take it to the next page because I'll show you another thing that we can do here. So if we just want to get molar mass by itself, then at this point we can solve for molar mass and find that molar mass is equal to mass times R times T over PV. And I'm just going to grab that equation and bring it over to the next page because that's where we'll finish solving this problem. Another thing we could do though, you'll notice we've got both mass and volume in here now. So I'm going to do something different in terms of how I rearrange this equation the second time. I'm going to take molar mass over to the left. So I've now got pressure times molar mass. And I'm going to take RT over to the other side also. And then I'm going to divide both sides by volume. And so by doing it this way, what do I have over here? Mass over volume. Well, that's just another term for density. So by making this substitution into our ideal gas equation, that number of moles is equal to mass over molar mass, we've now found that we can use the ideal gas law not only to find pressure, volume, temperature, number of moles, but if we have the right information available to us, we can even use it to find mass, molar mass, or density. And so let's just finish off this question that we started on. So molar mass is equal to mass, which was given to us in the problem, 0.230 grams, times our ideal gas constant, times the temperature, which was given in the problem is 298 Kelvin, over the pressure and volume. Now, volume was given to us as 125 milliliters. We can convert that into liters. And pressure, if you recall, was 765 millimeters of mercury. We need to convert that into atmospheres. So we use that there's 760 millimeters of mercury per atmosphere, and we get 1.02 atm. Finally, we can just finish by solving the problem here. And we get a molar mass of 44.1 grams per mole. So as you can see, a lot that we can do with the ideal gas law, and that's what we have all of these equations for. With just a little bit of information about a gas, we can go in many, many different directions.